All right, grade 10s, we're going to continue our discussion of motion by talking about the difference between speed and velocity today. So speed is a scalar quantity, whereas velocity is its corresponding vector, which requires direction. So our definition for speed, the average speed is defined as the total distance an object travels divided by the time elapsed, or the time between when it starts and when it stops. All right, so it gives us this formula in words: average speed is equal to total distance over the total time, which simply reduces to V is equal to D over T. Remembering that speed is a scalar quantity that doesn't require direction, and we're not putting any vectors over top of those quantities at all. So it's pretty straightforward. Whereas velocity is the time it takes for an object.
It looks like the internet is now back up and running. Thanks.
All right, sorry for that interruption. Velocity is the time it takes an object to undergo a displacement in a certain amount of time. And remember the difference between displacement and distance. Displacement is a vector and it requires direction. So the average velocity is a rate at which your displacement occurs. This time, it's got a very similar formula to speed. We use the same symbol V, but we put an arrow over top of it to distinguish it from speed. So velocity has that arrow. Again, remember, sometimes you're going to see X instead of D, but when I do my problems, you're going to see a D, which remember indicates a position. So, but if this was on a grid, X would be your horizontal movement. So remember, our friend delta here means change in. So it would be change in position, which is displacement, over the change in time. Now remember, whenever we have change in, the change implies that there is a final position and an initial position. And remember, we're going to take the final position and minus the initial position, which is displacement, and we'll take our final time minus the initial time of the motion. Quite often the initial time will be 0. Now in terms of a direction for your velocity, it's going to be the same as the direction of the displacement. And remember, we're not going to be worried about a sign for a time interval for delta t, because it's always going to be positive. Remember, our directions can be north, south, east, or west, but we get to decide what we're going to give as the positive direction, and then the opposite direction would simply be the negative, just like before when we were working with displacement. Now our units for velocity in the metric system are either meters per second or kilometers per hour. Now other units may be given to you in a problem, and generally you will need to convert them so that they will end up being meters per second or kilometers per hour, right? So to convert, if we happen to want to convert from meters per second to kilometers per hour, you would multiply your meters per second by 3.6 to get your kilometers per hour. Consequently, if you were going to go backwards and go from kilometers per hour to meters per second, you want to divide by 3.6. Now, to get a little more of an understanding about the difference between speed versus velocity, let's take a look at this diagram right here. Both cars start at the same place, point P, and they end at the same place, point Q, but one car has it would be a speed, and the other car is represented by a velocity. Hopefully you can figure out which one's which. Remember that the car, and let's assume they do it in exactly the same amount of time. But we can tell that the blue car covered a greater path. And remember, that would be its distance. And so if we wanted to use the blue to represent the motion, we would be calculating speed, because speed is the distance, and remember, distance does not rely on a straight line, it relies on your total path divided by your total time. So the blue line is representing the speed, or average speed of a vehicle, whereas the orange line would be representing a velocity. Because remember, a straight line distance from where you start to where you finish represents displacement, and when we take displacement and divide by the time interval, then we get velocity. Right, so essentially, if we finish out the slides, that's what it says. So let's look at some problems working with speed and velocity. So let's say the question says here, a stunt rider, stunt bike rider goes 39 meters in 3 seconds. How fast is the cyclist riding? So we're not given any indication about direction at all, and the term how fast, it's very general, so we're trying to find its speed, and no direction is necessary. So remember, we had a formula to calculate speed. Speed is equal to distance over time. Our distance given is 39 meters. Our time is 3 seconds. Very straightforward question. Speed is equal to distance over time, 39 meters over our 3 seconds. That reduces to 13 meters per second. So the final statement is that the bike rider is going 13 meters per second. Now, quite often we don't think in terms of meters per second to have a grasp on how fast or slow that motion is. We often relate to kilometers per hour better because that's what our speedometers are going to tell us in our vehicles. So what if I wanted to convert my meters per second to kilometers per hour? Multiply by that magic number 3.6. So 13 times 3.6 is rounded to 47 kilometers per hour. And of course, that's the legal maximum speed limit on a typical Calgary residential street, right? 50 kilometers per hour. So it gives you a better sense on how fast this bike is going. Now, this second problem is going to be a different kind of question because our starting point is not 0. It's not 0 seconds, and it's not at the 0 reference point. So this is a race, a bit of a sprinter example. The sprinter leaves the starting line and passes a 12-meter east mark at 1.8 seconds, and then passes the 56-meter east mark at 6.7 seconds. So somebody's standing there, and they're timing this runner. What was the sprinter's average velocity between the two positions? All right, remember sometimes a diagram is helpful. So we have our starting line, which would be our 0. Now we have to assume that I'm making to the right east. So I've defined my east as a positive direction. So I've got a line here representing sort of our first position. And our first position is 12 meters. We could call it our initial position. That we care about, because what we care about is not the whole average velocity. We only care about the average velocity from the 12-meter mark to the 56-meter mark, which is the final position of the sprinter. So this timer gets 1.8 seconds, this timer gets 6.7 seconds. So we need our formula for velocity. So velocity with our arrow to represent that it's a vector is equal to the displacement. So remember, now I have my old friend delta D with the arrow on top for displacement, divided by the time interval, which is the change in time. So to flesh this out a little more, delta D is final position minus initial position over the final time minus the initial time. So our final position is at 56 meters east, so positive 56, minus our positive 12. So that's simply 56 minus 12, divided by the final timing, 6.7 seconds, minus the initial timing of 1.8 seconds, reduces to 44 meters per or over 4.9 seconds. So we do the division on our calculator. It rounds to 9.0 meters per second. Your calculator will be like 8.97. But we're going to round it to 2 digits. 9.0 meters per second. Positive, which means with our sentence here, the sprinter has an average velocity of 9 meters per second east, because positive was defined as our east direction. Again, to get a rough sense of that, you could multiply by 3.6, and this, by the way, is a pretty fast sprinter. 9 times 3.6. So sprinting at about 32 kilometers per hour, so roughly the speed a car goes in a playground zone. Last question here. Let's say we were asked how long would it take a car to travel 140 kilometers if it was moving with an average velocity of 25 meters per second. So this time we are working, really this could be a speed question. Direction is actually not going to be terribly significant because we're asked for time, and time is not going to have a positive or negative value. So we could treat it actually more like a speed question. So what have we been told? The distance the car is traveling is 140 kilometers, and the speed or velocity is 25 meters per second. So we are trying to find time, and I'm going to find time in seconds. Now to find time in seconds, guys, very important in physics, when you use a formula, you must make sure that your units for, say, distance or time are the same. So we can't really do a problem where we're working with kilometers and meters. So we do have to do a unit conversion, and I've decided to take my 140 kilometers and make it into meters. So there's 1,000 meters in a kilometer, so you have to remember your metric conversions. So multiplying by 1,000, we get a 140,000 meters with our speed of 25 meters per second. So you have to rearrange your formula to solve for time. Remember that velocity is equal to distance over time, or speed is distance over time. So if we want time, that is the distance over the velocity. So that's why we're going to put 140,000. Now I'm getting sloppy, I'm not putting my units in here. So remember that this is meters, and this is meters per second. When I simplify on my calculator, I get 5,600 seconds. But again, that is hard to relate to because we don't usually talk about our timing in thousands of seconds. So to put it into something we can better relate to, let's change our seconds into minutes. I'm taking for granted that you know there's 60 seconds in a minute, so I have simply divided my 5,600 by 60 to get 93 minutes. And 93 minutes, if you divide that by 60, would give you about 1.6 hours. So now we have a really good sense on how long it would take this car to travel 140 kilometers. All right, in the next lesson, we're going to talk about how we can graph velocity and understand its motion in that way.